I am Laura Freijeiro Gonzalez, and I am going to talk about a work I developed jointly with my PhD supervisors, Wenceslao González Manteiga and Manuel Freijeiro Gonzalez. So I think I can hide this. Yes. Okay. So we have summarized this article, this work in an article called A Critical Review of Lasso and its derivatives for variable selection under dependence among covariates. So first of all, just 1 minute. Okay, I don't know why I can pass to the second slide. Oh, okay, it's in the end. Now, okay, sorry. Okay, so first of all, I want to give a short motivation for our work. If we are in a case that we have a P covariates, which we denote by x1, xp, and we are interested in explaining a variable of interest, why it is quite common in statistics to want to implement a first variable selection step when only the relevant covariates among the P available ones are selected and noisy ones are discarded. In order to perform this selection step, it is quite common to make use of the regression models. In this way, we have that by means of a functional M, we know the structure between the P explanatory covariates, here summarized in a vector of P dimension, and the variable we are interested on, denoted here by Y. So if we assume the ISIS framework, which is the well-known multiple linear regression model, as the name suggests, we have a linear relation in terms of the P explanatory covariates by means of an unknown beta vector, plus an observable error in practice, which we denote by bar epsilon. So if we want to perform this selection step, we can estimate the beta vector and select only those covariates which are significantly not equal to 0. For this purpose, we can make use of the ordinal least square estimator, which has the expression given in the slides. However, there are some limitations in practice, in particular when we have that the number of covariates P is greater than the sample size N. This problem is intractable, so we cannot estimate the beta vector. This is related with the non-invertibility conditions of the X transpose X matrix. And there are other situations where we have problems too. For example, when we have a strong dependence between covariates, and again, there we cannot invert the X transpose X matrix. In order to relieve these problems and to give alternatives, in the literature, it is quite common to add a penalization to the OLS problem. This penalization is given by a P functional, which depends on a regularization parameter lambda, which always take values greater than 0, and is applied over the beta vector. One of the most employed penalizations displays to the well-known Lasso regression. This implies a L1 type penalization of the OLS problem. This means that this imposes a penalization on the absolute values of the coefficients of beta. As I mentioned before, this is ruled by the penalization parameter lambda, which always takes value greater than 0. This estimator allows us to estimate the beta vector of the linear regression model when we have more covariates than samples in the P greater than N framework. And at the same time, we can perform covariate selector. This is because the sparse nature of this estimator. Then we can only take into account those covariates which beta G coefficient is not equal to 0. However, this procedure has some important limitations in practice. Here we have summarized these limitations in 4 blocks, denoted by bias, inconsistency, FDP of full discovery proportion, and the correct selection of the penetration parameter lambda. In terms of the bias, it is well known for the Lasso that if we have more covariates than sample size, the model can saturate after selecting n covariates. This is related with the type of optimization algorithm employed to obtain the estimation of the beta vector. For example, making use of algorithm as the coordinate descent, which is implemented in the famous GLMNet package of R, allows all the covariates to enter the model. However, other alternatives, as the large algorithm, only admits n covariates before saturating this model. Moreover, related with the number of covariates included in the model, the Lasso estimator is always biased. This can be easily explained in the orthogonal design. If we denote here by hat beta alls, the alls estimator of beta, and we can see as this estimator is shrink by the lambda parameter, in the sense that when the absolute value of the beta alls estimator is greater than the penetration parameter, we rank this value for the value of lambda. Otherwise, this takes the value 0. As we know that the beta alls is an unbiased estimator, we can then deduce that the estimator of the Lasso regression is biased. Besides, we have some drawbacks related with the consistency of the algorithm. If we denote by S the set of true relevant covariates, and we estimate it by the hat S, it is necessary for a consistent algorithm that for this to be capable to correctly recover the set S. This is translating the condition that the probability of recovery in the true set of covariates tends to 1 as the sample size increases. This places a restriction in the sample size. In particular, it is necessary a sample size greater than the cardinal of S, number of relevant covariates, times the logarithm of P. In the framework, when P is greater than N, this sample size it is not always available. So especially in these frameworks, when we make use of the Lasso regression, so we cannot always guarantee the consistency for this procedure. Moreover, this procedure requires other important assumptions too. We can distinguish between 2 different types of assumptions. The first one is related with the structure of the covariates matrix. Here, XS denotes the submatrix of X, taking into account only those covariates belonging to the S set, and similar for the beta vector. So conditions as the representable condition are needed in order to guarantee a good performance for the Lasso. This condition is related with a good structure of the data in order to be able to discern between the relevant covariates and the relevant ones. Correlated with these conditions, there is other types called beta mean conditions. This places a restriction in the beta vector. In particular, we place a restriction in order to be able to recover the true signal. For this purpose, we ask for the infimum value of the true set of covariates, yet the beta sub G value with zeta in S be greater in absolute value than the square root of the cardinal of S times the logarithm of P divided by the sample size. If we can assure a good performance of the lasso, we have other limitations in practice. These are related with the correct recovery of the set S. It is known that S is a trade-off between the false discovery proportion, the FTP, and the true positive proportion, TPP. This means that if we can to assure a proper recovery of S, it is quite common to have to add a noisy covariates in order to be able to correctly recover this. So as a result, we have not performing covariate selection well. Eventually, one of the most important parts of a lasso adjustment is optimal selection of the penalization parameter. However, this is quite difficult in practice because if we want to take an optimal lambda value, minimizing the mean square error, it is known that it is going to depend of the variance of the linear regression model error, denoted here by the lowercase sigma. In order to solve this inconvenience, it is quite common to make use of cross-validation techniques. However, these techniques cannot be optimal in terms of covariate selection. Maybe we have to add fifth block and to say that for a good performance of the lasso, it is a requirement that all covariates has to be in the same scale. In other case, the penalization of the lasso regression is not going to be fair because covariates with a high scale are going to have a strong weight in the penalization part, and others with a lower scale are more likely to enter the model. In this point, we have seen that the lasso has important limitations in practice, that the lasso performance is not optimal even in the orthogonal case under independence. So we wonder what we can expect under dependency scenarios. We know that the lasso is not going to perform well, but we want to know what to expect, how the lasso performs in those cases, and if there is other algorithms or modifications which can perform its behavior. For this purpose, in our work and in the article, we propose a simulation study under different dependence structure. For this purpose, we are going to consider the independence case and then two dependence scenarios, quite tricky. And we are going to analyze the results of the lasso and of other techniques. Then we simulate under the multiple linear regression model. We assume that our covariance matrix is normal with covariance matrix sigma. Our error of the model is normal too. And the variance of this error is allowing to explain at most the 90% of the deviance of the model. We are going to take as p equal 100, and we always assume that the relevant covariance, the lowercase s, is always less than p. So we are going to try with different sample sizes and with different different force of dependence. So first of all, we test the performance of the lasso in the orthogonal design. In this scenario, we assume the relevant covariates located in the first S placements, and the covariance matrix is the identity. as the number of relevant covariates, we assume this to be 10, 15, and 20. So next, I am going to show a brief summary of the simulation results. For the dark blue areas, we have the relevant covariates selected by the algorithm. For the soft blue areas are noisy covariates selected by this. And in the table, there are a summary of the mean square error and the percentage of deviance estimated by this model. The dashed lines mark the value of S. So yes. If we adjust the lasso, making use of the lambda, which minimize the mean square error, we can see that even in the orthogonal scenario, this performs quite bad, in the sense that this adds a lot of noise, even more noise than relevant covariates in some cases, and overestimate a lot the results. So one thing I forget to mention it before, is that we have a test with different sample sizes and different cardinals of S in order to verify and do not the consistency conditions for the lasso. In this point, we asked...
May I have a question, actually?
Yes.
I have some, maybe something it's not perfectly clear for me. Maybe I'm not sure if it's in this slide or in the other slide, because so in your case, P equal 100 and okay, N equal 25, for example. So what's exactly for you orthogonal design? Because do you mean, yeah? Do you mean that exactly colon of X are exactly orthogonal, which can appear only when N is larger than P? There is something which is not completely clear, actually, for me.
Okay, for the orthogonal case, I am here. I am assuming that my covariance matrix is the identity. So I have a orthogonal covariates. And in order to be fair with other algorithms, and because the lasso asks for this condition, I am going to standardize the covariates in a univariate way always. I mean, in this scenario, it is necessary, but then in the dependency structures, I need the covariates to be in the same scale. Just to perform the lasso in the usual way, I am going to standardize those covariates in a univariate way.
So I have a question. Like, how do you select lambda for this plot? So what type of
in order to perform lasso, I have make use of the GLMNet library of R. So our first choice is to select the penetration parameter as the value which minimizes the mean square error.
Thank you.
In this case.
Okay, so for me it's okay. In general, actually I have in mind that orthogonal design means X prime X is exactly equal to identity, but in your case it's something different. So now I understand. Okay.
Okay, perfect. So one more thing is that I'm implement adjustment in 2 steps. In a first step, I implement a lasso regression in order to select covariates, and then in order to avoid a bit the overfitting, I compute the beta odds estimator with those covariates selected by the lasso. So in the table, I show the results after estimated beta by the odds problem. So
can I just ask, so are you using cross-validation then to select your lambda?
Yes, I implement a cross-validation, yeah, minimizing the mean square error, true. Okay, so in view of the results, we ask if maybe a larger value for lambda is required in order to avoid noise. So we try with larger values of lambda. I have only here one option. And we decide to take the lambda value, which is larger than lambda mean. And this is taken as between one standard error of the lambda mean. So we have a larger value of lambda, and we can appreciate as the selection of the lambda value decrease the number of noisy covariates included in the model and corrects a bit the estimation of the Lasso mean. However, we can appreciate as this procedure keeps adding a lot of noisy covariates into the model. So maybe a larger value of lambda is needed, but in practice it is quite difficult to establish which value of lambda is the optimal one, because we need some criteria in order to decide the penetration value. So we have decided to prove with other type of selection of lambda. For this, we propose to select lambda, minimizing a global criterion as the big. We know that the big doesn't perform well in the case of p greater than or equal than n, but we want to see, at least for n equal than greater p, how this algorithm is going to select the covariates. So we can see selecting the lambda, which minimizes the big, we take very good results for the case of n equal than p, but horrible ones for p greater or equal than n, even worse than the Lasso ones in some cases. However, for larger values of n, this corrects the overestimation made by the Lasso judgments. So in this point, we have seen that the Lasso performs badly under orthogonal design, under independence. So we want to compare its performance under dependence with other methodologies in order to test if we can improve its results. So we have revisiting the existing literature, and we have made a selection. There are a lot of procedures which search for the selection of covariates, but due to extension, it is impossible to include all of them. So we have taken under consideration those which have proved its efficiency or guarantee good properties. So we have considered different options as weighted versions, resampling versions, or discordant versions, apart from alternatives or modifications of the Lasso. In practice, we have tested only with the highlighted algorithm. This is because we have found out that the resampling versions have a high computational cost in practice. And in the case of the three-scoped versions, we have another difficulty. This is related with a proper selection of the three-scope, not only a proper selection of lambda, but now a selection of an optimal value for the three-scope. So here, the algorithms considered are the SCAF algorithm of 5 and the adaptive Lasso of 2. Both performs a bias reduction and improve the selection of covariates. Besides, we consider the Dante selector of Candace and Tau, which is consistent to orthogonal transformations. Besides the relaxed Lasso, which guarantee faster convergence rates and better predictions, the square root Lasso of Belloni, which is able to take an optimal value for lambda without knowing in advance the variance of the error, the scaling Lasso of Su and Zhang, which iteratively estimate the variance of the error and the beta vector, and eventually the distance correlation algorithm for variable selection of Freijeiro. This implements iterative forward selection, making use of the correlation of distance. For this aim, this borrows the idea of the large algorithm of Ephron in order to select the relevant covariates in each step. So taking under consideration these algorithms, I am going to quote the reference later if someone is interested of some of them. And then now I'm going to first of all display the R libraries employed to adjust these algorithms. We have also searched for algorithms with implemented code in R libraries to implement them. So these are the selected algorithms with the related libraries. Again, I am going to give the reference at the end. And now I am going to test to compare the performance of the three Lasso we have three Lasso proposals with these algorithms. So we can see as all the algorithms considered outperforms the Lasso behavior. We have here the simulations for the better case, taking n equal 400. And we can appreciate as all of them are able to recover the complete set test. Maybe not the damping selector for s equal 20, but the remaining ones, yes. And all of them recover the set S and avoid unnecessary noise. Maybe we have to exclude the adaptive lasso, making use of the lambda mean, the lambda which minimizes the mean square error. So next, we're going to test.
Can I just ask something before you continue? Do you have any results? Have you tested scenarios where you have more noise, like a lower signal noise ratio?
Sorry, could you repeat again?
So have you tested any scenarios where you have, I mean, so it seems like the simulations you tried here, you have a design where you expand a lot of the variance, so 90% of the deviance, for instance.
Yeah.
I was wondering if you have tried some scenarios where you have more noise than this.
No, we have chosen the noise in order to display the 90% of the deviance with the objective of being able to test how the estimations of the model is. I mean, we are going to search for algorithms able to recover the relevant covariates, interpreting the dependence structure of the data. But at the same time, we want to know how they perform in terms of estimation. So we have decided to calculate the mean square error and to calculate the percentage of deviance. As we have fixed the 90%, we know that if our algorithm exceeds this value, it is overestimating the model. For example, in the Lasso case, we have seen this phenomenon.
Okay, thanks.
Okay, so next we are going to test the behavior of the different algorithms under dependence structure. We start with a dependence by block type of correlation matrix. Here, we assume that the covariates are correlated in terms of moduli 10. I mean that if in two locations they are equally moduli 10, they are going to take the correlation value equal rho, with rho taking the value 0.5 and 0.9. Again, we assume that the relevant covariates are in the S first locations, and S takes again the values 10, 15, and 20. So in case of dependence, we can see that things change. Not all the proposed algorithms are going to perform well, and it is going to depend on the type of scenarios we are working with. In case of the dependence by block, taking rho equals 0.5, we can see as again the Lasso types overestimated the model, add a lot of noise, but there are other algorithms which have a similar behavior than the Lasso, as the damping selector and the square root lasso. We can appreciate as this type of algorithms try to completely recover the z-test, the dashed line. In contrast, the continuous line marks the number of true relevant covariates in order to give a good explanation of the data. I mean, in case of having s equal 15 or 20, there are not really necessary all these covariates between the structure of the data. It is enough with 10 covariates, and 10 is the location of the continuous line. So we can appreciate that algorithms as the Lasso versions, the damping selector of the square root lasso, always search for the complete recovering of S, but other algorithms made a smarter selection, as the adaptive lasso versions, this CAD, the relaxed lasso, scaled lasso, or distance covariance for variable selection. Besides, we have to make one more distinction between, we can see as only the adaptive lasso versions and the SCAD are able to select 10 out of the P relevant covariates, 10 out of the S relevant covariates. But other ones, as the relaxed lasso, scaled lasso, or distance covariance for variable selector, interchange relevant covariates with noisy ones. However, they perform well too, because we want a subset of length 10, which is a representative subset of the 10 relevant covariates. And these noisy ones covariates included are interchanged with relevant ones which have not been already added to the model. So maybe it's a bit confused. I can repeat if it is not understand. So, okay, we can appreciate this. We can see as the algorithms keeps overestimating the model, but some of them are able to correct a bit the overestimation made by the lasso. But in this case, it is quite difficult for the models to correct this overestimation. We can appreciate the same phenomenon if we take a strong correlation, taking rho equals 0.9 in this case. Again, we have to highlight the adaptive lasso versions and the SCAD algorithms as the best options. Eventually, we test in other different dependent scenarios. In particular, we consider a double-place covariant structure. Now, the correlation is given by this expression, and all the covariates are going to be correlated between them. Based on the type of dependence, we consider two different scenarios. The scenario 3.8, where the relevant covariates are placed in the S equal 15 first locations. So we expect for smart algorithms, in this case, to select the first covariates with the high probability, and maybe to interchange some of the last S equal 15 covariates with noisy neighbors, because the correlation it is going to be strong, especially for rho equals 0.9. In contrast, in the scenario 3.b, we have only 10 relevant variables. They are placed every 10 sites. For example, in the first location, 11 to 91 location. And in this last scenario, we expect for smart algorithms to be able to recover the 10 relevant covariates, or at least a representative subset of these 10 relevant covariates. So we allow to interchange noise covariates but by relevant ones, but we want to being able to have the information of these S equal 10 relevant covariates. So for this purpose, we again test for rho equals 0.5 and 0.9. So We start testing in the scenario 3.8, where we have the relevant covariates in the 15 first locations, and due to our two-place covariance structure, we know that all the covariates are related between them. This scenario is quite tricky. We can appreciate as the most part of the algorithms fails to correctly interpret the data structure. So, for example, Lasso versions, especially the Lasso with the lambda minimizing the mean square error, the Lasso mean, and others as the adaptive Lasso mean, the SCAF algorithm, even the relaxed Lasso, square root Lasso, scaling Lasso, fails to correctly interpret the structure of the data and try to recover the complete set of covariates, but adds a lot of noise. However, there are other algorithms which try to interpret the structure of this covariance matrix as the adaptive Lasso, taking lambda between one standard error, the damping selector, and even we can include the distance correlation for variable select. These three algorithms doesn't take into account 15 covariates, but a small subset of them. Especially, we can appreciate this phenomenon taking rho equals 0.9. This is because the covariates are highly correlated, even the relevant ones. So with a small subset of these covariates, we can explain the dependence structure of the data. In order to know if those algorithms are selecting well this subset of covariates, we have calculated the number of covariates required to explain a high percentage of variability of the model. And we have find that all these three algorithms, that Lasso, damping selector, and distance correlation for variable selector, are able to take into account this number of covariates. So they are performing a good selection of the relevant covariates. Next, if we simulate under scenario 3.b, where relevant covariates are placed every in 10 locations, we can appreciate as almost all procedures have a lot of noise trying to recover the complete test. Only one algorithm is able to correctly recover the set S without interchange relevant covariates for relevant ones. Others, maybe as the distance covariant for variable selection, in the rho equals 0.9 case, interchange relevant covariates with irrelevant ones, but it is true that they are able to completely cover these 10 covariates, interchanging relevant ones for noisy ones. So its performance is good too in order to interpret the dependency structure of the data, although they are not able to take 10 covariates out of the important set. So just to conclude, I want to give a brief discussion about the simulation results. So we have to say that for a good performance of the Lasso under independence scenarios, it seems that a good choice of lambda is needed, in particular a larger value of lambda, than lambda mean. But this is quite tricky in practice because we need some minimizing or maximizing criteria in order to choose a value for lambda. And we don't know in advance how to take this optimal value. Moreover, all the alternatives considered have proved to improve its results in this independence context. We can highlight here the adaptive Lasso 1C, the relaxed Lasso, the damping selector, and the distance covariant for variable selection. In case of dependence structures, things change. In particular, we know that the Lasso has a deficient behavior, but not all the proposed methodologies performs properly. Only the adaptive Lasso 1C and the distance distance correlation for variable selection seems to be competent in all the scenarios. Maybe they are not the best ones, but are really competent in all the dependency scenarios proposed. The SCAF performs well under structure by blocks, but fails in the case of the Toeplitz covariance framework. Inversely, with the damping selector performance. And the relaxed lasso, square root lasso, and scale lasso present a deficient behavior too. So here are the reference of the other approaches employed in the simulation study, the reference of the IR libraries, in case someone is interested of this. This is also, thank you so much for your attention.